Hello and welcome to Stars, Cells, and God. This is the show where we discuss new discoveries that are taking place at the frontiers of science, the ones that have theological and philosophical implications, as well as new discoveries that point to the reality of God's existence. My name is Jeff Zweerink. I'll be your host today. But before we get into the discussion, I want to encourage you to subscribe to our channel, Reasons to Believe. Click on the bell icon so you can be informed of new videos. Learn more about us at reasons.org or following us on social media at RTB_official. Well, let's get into our show today, Hugh. I know you've got a discovery on star clusters, so why don't you go ahead and kick it off for us?
Well, it's all about the birth of the solar system, and it's based on two research papers, one published in Astronomy and Physics, the other one published in Astrophysical Journal Letters. And neither one of the sets of authors refer to each other, but the two research studies are highly related to one another. Mm-hmm. And the bottom line is it's giving us new insights on the fine-tuning that's necessary in the birthing of the solar system to make possible the future existence of life, and especially advanced life. And so the first paper in Astronomy and Astrophysics is an attempt to determine with more precision the number of stars that had to be in the solar system's birth cluster. And astronomers have known for some time that the solar system had to be born in a fairly large star cluster. It's necessary in order to explain the heavy element abundance we see in the Earth and in the solar system in general. And what this team of astronomers attempted to do, team is just two astronomers, is they measured aluminum-26 in the primitive meteorites in the solar system. So, there's these chondritic meteorites that we know are the residues of the very first assembly of, gas and dust to make the solar system. And so they're able to measure the decay. Aluminum-26 is a radiometric isotope that decays quite quickly, just in a couple million years.
That's an astronomer joke there. It's quite quickly. It's only a few million years.
Only a few million years, right? Well, the problem is you can't directly detect the aluminum-26, but you can detect the daughter products of the decay of aluminum-26. And so by that means you can determine how much aluminum-26 had to be in the birth cluster. And aluminum-26 comes from core collapse supernova eruptions. And
So presumably the implication of that is our star is kind of isolated off in its own environment right now. If it's got aluminum-26 decay products in it, it had to be in relatively close proximity to a supernova that was producing this when it was born.
Right, and especially a core collapse supernova.
Right.
Because what they were measuring was a quantity of aluminum-26 that was so high, it meant that the early solar system had to be in close proximity to a core collapse supernova eruption event. And these are relatively rare supernova eruptions. Mm-hmm. They're the least common of the, and it takes a really massive star to end up as a core collapse supernova eruption. But it's those events that produce a huge quantity of aluminum-26, mm-hmm. and not only aluminum-26, but a whole array of the heavy elements we see in the periodic table. And, our Earth is particularly rich in those elements. Mm-hmm. Good thing, because that's necessary for advanced life. And so what these two astronomers did is they measured as carefully as they could the quantities of aluminum-26 in these primitive meteorites, and then used that to determine, okay, what's the minimum size of the star cluster in which the solar system was born, and what's the maximum size? And the number they came up with is that the minimum was the solar system had to be born in a dense star cluster with at least 2,000 stars.
So how did they get to that? I mean, I have a guess at it, but why couldn't it just be that the sun was formed out of a gas cloud that happened to have a star passing by that went supernova like that? Why does it need to be such a large cluster?
Well, in order to get a core collapse supernova eruption event, and that's kind of what's in more detail in the second paper, Astrophysical Journal Letters, is that you need a special kind of dense molecular cloud. It has to be particularly dense, and very large. Large enough that you get these filament structures inside the molecular cloud. And if you've got several filaments basically coming together to make a hub, that produces a site where you can get a star massive enough forming that it'll burn up quickly and end up as a core collapse supernova.
Okay, so you're basically doing statistics on saying we know that the sun has to be in the vicinity of this kind of star.
Right.
How big do things, or what's the environment where these sorts of stars form?
What stars form. So, if it's a small molecular cloud, not that dense, these things won't even happen. And so we know it has to be a big enough molecular cloud and dense enough that you've got the possibility of these core collapse supernova forming in close vicinity to the emerging solar system.
Okay, so you've got a gas cloud that is, one odd phenomena, since we're kind of an isolated star out in the middle of nowhere, if you will, a long ways away from anything, the idea that we form in a star cluster is a little bit unusual.
It is.
But the fact that there's this aluminum-26 says this core collapse supernova has to be around, which means that we formed in a gas cloud that formed thousands, somewhere on the order of 2,000 or more stars, and we were part of that, or our solar system was part of that environment when it was first born.
And, I got a couple of slides here. The first one basically shows you a star cluster with about 2,000 stars in it. And so this would be like, and you can see how densely packed the stars are together and how in the core of the molecular cloud, you do get these massive stars that can become core collapse. The second slide basically shows you, okay, this is at the top end. So
what do you mean top end?
20,000 stars.
Okay, so this is a really massive cluster then.
Yes, and it's kind of like, it's basically a small globular cluster. I mean, globular clusters range from 25,000 stars up to several million stars. So this would be the low end of a globular cluster. And people say, well, one thing they address is we know it can't be more than 20,000 because if you've got more than 20,000 stars, you're going to have several of these core collapse supernova eruption events, and this is going to cause problems for the disruption of the solar system's planets. So they said 2,000 minimum, 20,000 maximum. And
so do you know off the top of your head, so we're about 4 light years away from the closest star. So on the order of 5 to 10 light years away is our star distances right now. Inside a cluster, what are the distances? Do you know that off the top of your head?
Yeah, I mean, if you're talking 2,000 stars, that means the nearest stars are going to be less than about a light year away.
Okay, so significantly denser than what we are.
Yeah, if you're talking 20,000 stars, they're even closer.
Okay.
Which is why you can't go above 20,000, because you go above 20,000, the density is so great. There's so many really big stars, that's going to cause problems. And what this paper...
So presumably, if we were in a cluster that was that size, we would have seen more. I mean, presumably, you would have seen more aluminum-26 or something. We would measure the consequences of having been in a star cluster that large, or is that incorrect?
Well, that would be true, but the real problem for life is that when you got that density of stars, that many massive stars around, the radiation you get, I mean, globular clusters that big form intermediate black holes, which is going to be a problem. And so we wouldn't expect the solar system to survive with its array of planets with the stable orbits that they have. So that's where they get the upper limit.
Okay, very good.
And, this sounds like not too constraining, 2,000 to 20,000, but it's the first time that they've been able to constrain the size of the sun's birth cluster to within a factor of 10.
Okay.
Before it's like a factor of 100. So this is a big advance.
So it's okay, very good.
And the second paper published in Astrophysical Journal Letters was making the point that we now know that what facilitates star formation in these dense molecular clouds is the formation of these filaments, subfilaments, and nexus of filaments. And how if you want to get stars massive enough to form a core collapse supernova, you need several filaments that join together in a single spot. And so this requires, again, a fairly large star cluster. Basically, if you combine this paper with the previous paper, it's basically pushing the size of the birth cluster up towards 20,000, away from 2,000. It
Okay.
has to be big enough that you get these filament hubs so that you can get these.
So this sounds like it's putting detail. We know that the larger the star cluster, the larger the stars that are going to form into. I mean, it's just
Right.
kind of straightforward probabilities, if you will. But this is providing some detail on what is the mechanism by which those larger stars form.
Correct.
Okay.
So we know we have to be in a gas cloud where you're going to have several filaments coming together in a single spot so these big stars can form.
And big stars, what size are you talking about there?
We're talking like 30 to 60 times the mass of our star, the sun.
Those are pretty massive, considering
very
our star
massive.
is on the high end of masses anyway. So
Stars that are above 30 times the mass of our star, the sun, are very rare in our galaxy. They can only form if you get this nexus or hub of filaments coming together.
Well, and they last a pretty short period of time too, by
burn
being
up
so
quickly.
massive. So, on the scale of you're producing aluminum-26, which sticks around for a few million years, the star itself only sticks around for a few million years,
That's
if I remember
correct.
correctly. So,
That's correct, but that's an advantage because that means you get the necessary enrichment of these heavy elements early in the history of the solar system.
okay,
In fact, they're calculating that it happens within the first 100,000 years of the birth of the solar system. So that means that you need these really big stars to form early, and typically they do. They're the first ones to form. And then you need the solar system to form slightly later, because all of the necessary enrichment happens in the first 100,000 years of the solar system's existence. The other contribution, this has got a lot of authors in this Astrophysical Journal Letters paper, is that they've now been able to determine the solar system must form on a significant filament that streams away from a hub. And the reason for that is if you get the solar system forming too close to the core collapse supernova, it's going to damage the solar system in a way that's not going to make advanced life possible.
okay,
But being along one of these filaments, you can actually, the filament actually streams a flow of aluminum-26 and heavy elements towards the solar system. So it's
okay.
like
So
you've got
rather
a
than
highway.
rather than just being in the gas that's
Right.
blown out everywhere, it is kind of funneling it towards the Earth.
Yeah,
if you
it's
will.
like
okay, cool.
you got kind of like this little hose streaming
Right.
this stuff in. And what they determined is that to explain the enrichment we get and the stability in the positions of the planets orbiting the sun, it's necessary that the emerging solar system be along a particular kind of filament. Actually has to be one of the denser filaments.
Okay,
But it must be a single filament, but a high density end, so you get this efficient streaming effect. And you need the emerging solar system to be on the just right filament, just right size and density, and it has to be at the just right distance from the core collapse supernova to get the enrichment you need without destroying the solar system.
so why does it need to be smaller or larger? I mean, what's the consequences of something that's too small? Do we just get not as much aluminum-26, which
Well, that's the whole
that
point.
sort of doesn't seem to be such a big problem because that stuff decays away anyway.
Right, but when you get a lot of aluminum-26, that also correlates with lots of heavy elements that
okay.
are heavier than iron, which
Right.
we need for advanced life.
Right, okay.
We need them to be in high density. And so the filament must be fine-tuned in order that you get the right density. It has to be very high density, and you want the filament to be long. And that the length of the filament, the density of the filament, determines how efficiently this stuff is streamed in towards the solar system from the core collapse supernova eruption event. So that explains the fine-tuning of the filament, and you have to be at the just right distance in that filament compared to the core collapse supernova eruption event.
Why is that? Because it seems to me that you've got the core collapse supernova, it's funneling stuff away. Presumably the solar system is forming after the supernova went off. And
Right.
so kind of the destructive influence of the supernova is gone. Why do we need to be far enough away at that point in time?
Well, far enough away, because you need the supernova not to be so close that it's going to cause problems for future life in the solar system.
Okay.
And You want it to be on a filament that's able to, because the advantage of the filament is it takes all the stuff that the core collapse supernova is producing and streams it in a safe way to the emerging Earth.
Right.
And so if we were too close along the filament, you'd be impacted by the shock waves coming out from the supernova, the radiation coming out. You might wind up with too much aluminum-26. Too much aluminum-26 is going to cause problems for the gases that are around the planets. So that's where the fine-tuning comes in. That's been known before. That's not new. What is new is the fine-tuning of the filament that's necessary.
Well, okay, so what's the time scale on which the stars are forming in a cluster? Because you made a comment that these things form within the first couple 100,000 years of the cluster. So the bigger stars form first, they go off supernova. Are the other stars like the star that's the sun in our solar system? Do they form in similar time scales, or is it a million years or 100 million years?
I mean, it's one reason why you want to be on a G-type star. There's a lot of people saying, well, maybe K-type stars would be a good place for life.
Which are smaller stars.
Which are smaller stars, dimmer stars.
Right.
But those stars take longer to form.
Okay.
And so the G-type, this wasn't in the paper, but
right. No, we're just talking here.
We're just talking. But I think you're bringing up another fine-tuning point, is that the problem with an F-type star or an A-type star, I mean, and
those
again,
are the larger stars.
Larger stars, they form more quickly. G-type stars form a little slower, but they form more quickly than the K-type stars. But you're bringing up an interesting point. You want the solar system to be, the planets to be around a star that's forming at a rate that's going to be optimal for this enrichment without it being destroyed.
So you need something where the larger stars form more rapidly just because the gravitational pull collapse that facilitates that reaction. They're going to go supernova before the time scale where the star like our sun will form because it just takes longer. So presumably as 100,000 years plus a million years for, or whatever the time scale is for the supernova is going to be the time scale on which our star forms. Something like that is what's going on.
I mean, you want our star and the system of planets to be intact within 100,000 years.
Right.
And if you're looking at a smaller type star, it's going to take longer. So you won't get the necessary enrichment.
Okay, so our sun has to form after all of this stuff is blown out there so that it can be incorporated into not the sun necessarily, but into the planets, particularly Earth, which is going to need all of these other
But it needs
ones.
to form at the just right rate.
Gotcha.
So thank you for bringing it
up.
No,
okay.
That was good.
So that's part of why we need to be a little further away too, is so that our star is not disrupted in its formation. So it's a little calmer
That's
environment.
one of the advantages of forming along this dense filament. It allows the solar system to be far enough away from the core collapse supernova and yet get the necessary enrichment. So
does this stream play any role in helping to eject our solar system from the cluster? Because we are not in a cluster anymore.
No, you're bringing up a third point.
Well, of course. He's the one.
Yeah. And this is something I've written about in my books before. This, again, is not new, but this wasn't the subject of the two papers, is that you don't want to stay in that birth cluster.
Right.
Because, the stars are going to be too close. You're going to be exposed to the radiation from the big stars, the gravity from the big stars. You want to be tossed out of the birth cluster after you get the necessary enrichment. And you want to be tossed out quickly. And how do you get tossed out? Well, it's the same way we send, spacecraft to, Uranus and Neptune and Pluto. You get a gravitational slingshot. And so, when we want to send a spacecraft to a distant planet, we typically have it go around Venus and get Venus to do a gravitational slingshot to send it out more rapidly.
Right.
If you want to go to Mars in 6 months, you need a gravitational slingshot.
Okay.
And how do you get that gravitational slingshot? You get close enough to another massive body, and actually need several massive bodies. And so, like you've got the sun, the Earth, and Venus, for example, if you get the right configuration, it winds up giving a strong gravitational kick to the spacecraft. Well, astronomers argue the same thing must have happened with our solar system, is that it happened to be in a configuration where it was near some massive stars that in concert with one another wound up giving our solar system a slingshot effect where it was gravitationally ejected from its solar system.
Well, that would seem to argue for needing to have some larger stars in the cluster as well, because if we're the largest star, we're going to be doing the slingshot, not being the slingshot.
Well, it's another reason why we have to be born in a large star cluster, because only a large star cluster do you have any kind of possibility of the necessary slingshot effect. So the next slide I got here basically shows you what's happening in our Milky Way Galaxy, and basically shows you where our solar system likely was born, because we got a huge abundance of heavy elements, particularly on planet Earth, which means we need, so this helps us understand where the likely location of our birth star cluster was, about 4 kiloparsecs away from the center of our galaxy, where a kiloparsec is 3,200 light years. Because this is the place.
Where are we located today?
We're located today a little bit beyond 8 kiloparsecs.
Okay, so we've in this scenario, our solar system formed closer to the center of the galaxy and has drifted out to where we are now. Okay.
Yeah, we were about half the distance to the center of the galaxy when the solar system formed.
Would this abundance have been the case 5 billion years ago when the sun was being formed?
Yes.
Or would that dynamically change that much?
It wouldn't dynamically change that much, but the whole point is we have to be at that position to explain the huge abundance we have.
Okay.
But you don't want to stay there because conditions are not good there. And so this graph basically shows you where the solar system was born and where it ended up.
Right.
And what's interesting is it ended up at a place that's very underdense in heavy elements, which means it's also underdense in stars. I mean, it's something you brought up earlier.
Right.
We happen to be in a very underdense part of our Milky Way Galaxy where there's not a lot of nearby stars and not a lot of massive stars. And so,
well, and if I'm correct, that shows up in two ways. One, the further out you move from the center of the galaxy, the less abundant stars become. But also in the spiral structure, you can, even at the same radius, have denser and less dense regions. And I'm presuming we're in one of the less dense regions, even along the same radius.
Yeah, I mean, what's happening is that the center of the galaxy has a particular density of heavy elements, but it rises as you go up to 4 kiloparsecs.
Right.
Then it drops down to a minimum, and then it rises again, and then it slowly drops again.
Right.
And we're at that minimum that's just beyond the 4 kiloparsecs. So 8 kiloparsecs is where it does this and goes back up, and we're at the very bottom.
So if we were to try and explain our solar system formation, given our current location, we would struggle to do that because there's just not the amount of elements we see in our location to explain our star.
Right. But the bottom line is we formed in the most dangerous spot for life. We got the enrichment we needed for advanced life, and then we got tossed out and we ended up in the safest spot and the distance from the Milky Way Galaxy. So, that's what's, again, a fine-tuning thing. We were born in the most dangerous spot. We ended up in the safest spot. And you need a gravitational slingshot to eject us out from the dangerous spot towards a safe spot. But you also need a gravitational brake to stop us from continuing to go out.
Yeah, you don't want to be out in the recesses of space either.
And so it takes, in other words, we would have to wind up engaging a system of stars that would act as a gravitational brake and stop us from continuing to go out. And the next slide I got here.
But before we move off on that, one of the things that comes to my mind as we're talking about this is that, we talk about the universe being life-friendly, and the reality of it is most of the universe is rather hostile to life. It's friendly in that the carbon, the oxygen, the water, the materials necessary for life are abundant in the universe. But the vast majority of the universe is not particularly hospitable to life. What strikes me as interesting in your discussion here, one of the things is that we happen to have been born in one of those very inhospitable places.
Right.
The fine-tuning doesn't show up in how the universe looks, but in how we get from that inhospitable place to a place that is as hospitable as where we are.
Correct.
I just thought that was pretty remarkable. So.
It is. And so we wind up in this underdense region where we don't have to worry about gravitational disturbances.
Or other supernova. But it's also a place that's just inside the co-rotation distance of our Milky Way Galaxy. And that's what the last slide basically shows you. And that's the distance from the center of the galaxy where the spiral arm structure rotates at the same rate that a star orbits about the center of the galaxy, which means that you wind up with very few crossings of spiral arms. Right. When you cross a spiral arm, it won't be a problem for microbial life, but it is a big problem for advanced life. And so just because of the density of stars goes up, there's more larger stars, radiation, potentially
there's
supernova.
Also dense molecular clouds.
Gotcha,
right?
Yeah.
And every time we go through a spiral arm, we wind up getting the asteroids and comets disturbed in our solar system, which means we get a heavy bombardment rate. And we actually see that in the mass extinction events.
Right.
Every time we cross a spiral arm, we get a major mass extinction event.
Well, my recollection was that's even sensitive enough just if you take our oscillations above and below the plane of the galaxy, it gets more and less dense as you go through the center of the plane of the galaxy. And you can correlate that. There is some correlation with crossing the plane of the galaxy with extinction events.
That happens about every 30 to 35 million years.
Right.
But the really bad ones is when you get that happening at the same time you cross a spiral arm.
Yeah, that's a little rough.
And that's where you get the really big mass extinction events.
Yes.
Fortunately, right now, we're halfway between two major spiral arms. And so we're at the safest time.
So we've got a little while before we have to worry.
Before we have to worry. But that only happens if you're just inside the co-rotation distance.
Right.
Everywhere else, you're going to be crossing spiral arms more rapidly. So again, it's another fine-tuning argument.
Yeah.
Not only did we wind up in this underdense region, it happens to be a place where we very seldom cross spiral arms.
Right.
And so thanks to these two papers, this argument for the fine-tuning of the birthing of the solar system, I think has become much more detailed and much more persuasive in saying, hey, it looks like somebody was fine-tuning this to make sure that we can continue to publish these kinds of papers.
Well, and I liked another thing that stood out in your discussion is that, statistically speaking, we know that if you're going to have these kinds of stars, you've got to have larger clusters of stars. There's a mass distribution that just naturally plays out in there. But there's the mechanism by which it plays out, as we know more, actually puts in more of the details that points out some of the things that rather than just the statistical association, we're getting some of even the physical mechanisms behind it.
We are.
Which is, I thought, very fascinating. So,
and the other factor is you need to be in a just right galaxy that has the necessary population of star clusters of the right size, not too many, not too few. And so we happen to be in a spiral galaxy where we see just the right kinds of star clusters we need.
Well, very good. Any final comments?
No, that'll
or is
do
that
it. Yeah, I mean,
no, I appreciated that discussion. That was there's more detail than what we knew, and as we continue, I mean, as you said, the more we learn, the more reasons we do have to believe. I just see that play out there.
Since I knew I was doing this with you, so this is something Jeff is going to like. So.
Well, let's shift gears a little bit, and I just wanted to talk about a paper, as a summary paper published in Nature back in late June, but it was talking about not a detection of gravitational waves, but a strong hint of gravitational waves. And I just want to clarify that distinction in our discussion here so that it doesn't get missed in kind of some of the implications of it. But these are why it was talked about is that there are 4 different groups that have been measuring the timing of pulsar array. Or they look at various pulsars, and pulsars I'll talk about in just a second. But by monitoring a large number of these pulsars, we get very accurate timing of when the pulses come in. And by looking at the correlation of those pulses, we can make pretty remarkable measurements of distances and what's going on. And so that allows these astronomers to begin to say, okay, what can we tell? And the fact that 4 different groups are coming along and saying, hey, we see this same sort of thing, even though it's not quite at a detection limit, it's still interesting enough to put out there so that we can begin having the discussion, because it looks like as we continue to monitor, and this is programs that have gone on for 20 years, so it may take a while, although one of them is far more sensitive. I think it's the FAST one. It's a Chinese collaboration that has more sensitivity. They say with 3 years of data, they're able to put out similar sort of sensitivity. So they may get it a little earlier. But what they're finding are evidence of gravitational waves, a gravitational wave background in our galaxy, which the gravitational waves have a wavelength on the order of light years, so kind of something like a 10 to somewhere between 1 to 10 parsecs, if you will, which is very different than the gravitational waves that we were measuring with LIGO and the other Virgo and the instruments built here on Earth. Those have lengths of kilometers to miles. We're now talking light years, and so very different scale of gravitational waves. This is something on the order of the size of our galaxy, or at least distances between stars.
Is this based on them determining the population of pulsars and the rate at which the timing of the pulses is changing?
Well, so what they're doing in there, and I'll get to that in just a second, because well, I guess I'll go there now. So what you have in a pulsar is basically it's a very massive star, somewhere larger than 2 times the mass of the sun, probably 8, 9, 10 plus times the mass of the sun, that as it goes through its life, it explodes in a supernova event. What it will do is it will compress a fraction of this material down into a very small region, and that region will have about the mass, somewhere between 1 to 2 times the mass of the sun, but it will be compressed into something the size of a large city.
So we're talking like a neutron star.
Yeah, we're talking neutron stars. That's what that's what a pulsar is. And so instead of a sun the size of the sun, which is 1,000,000 times the size of the Earth, or a white dwarf, which is something the mass of the sun compressed into the size of the Earth, we're now talking something the mass of the sun compressed into the size of a large city, a few tens of miles across.
Right, and we're talking like a solid ball of neutrons.
That's effectively what it becomes, yes. Right. And so these, as you compress, just like a skater, when their arms are out, they rotate slowly. As they bring their arms in, they spin up faster. As you compress something the size of the sun down to the size of a large city, it's going to spin up, and these things will be spinning around hundreds of times a second.
Right.
They have very strong magnetic fields, again, for the same reason of just compressing it all down. And so what will happen is those magnetic fields will emit a beam of radiation, and as this thing is spinning around, we will see those beams pass by us.
That's why we call it a pulsar.
Exactly. That's why it's called a pulsar. Exactly.
Yeah.
Now, what's fascinating about this is because it's effectively a ball of neutrons, they're very stable. I mean, there are small changes that happen, but they're incredibly stable. And so we can use these as clocks to figure out what's going on. And that's what these arrays are doing, is looking at an array of these pulsars and correlating the time between all the different pulsars. And because of how accurate and reliable these pulsars are, and by looking at a large enough of them, what astronomers were able to calculate, or looking theoretically, they can say, if we just look at the correlations between all these things, if there are gravitational waves passing through which distort the shape of the space in our galaxy, we should expect to see this. It's a Hellings-Downs curve, and I'm not going to go into the details. You can go look at the paper if you want to figure out what a Hellings-Downs curve looks like and how it's derived. But it's basically a way of measuring there are distortions in the shape of our galaxy that would be caused by large gravitational waves scattering or a bunch of gravitational waves from a bunch of different sources coming through our galaxy. The analogy would be throwing a bunch of rocks or rain onto a smooth lake. You're not going to measure the waves from any particular impact, but you can measure the effects of all of the waves coming across. And that's effectively what they're measuring here. And these waves...
Okay, let's get explicit here, because we're talking like thousands of pulsars.
Right.
How do the gravitational waves affect the pulsars?
What effectively happens is as the gravitational wave comes through, it distorts the shape of the galaxy.
Yes.
Now, when we're looking at it here on the Earth, we're using kilometers, and these things have distortions on the order of 10 to the minus 20, 10 to the minus 19. So on 1 meter, you're measuring 10 to the minus 19 meters is what you're trying to measure. So that's why LIGO is 4 kilometers long, because it makes that longer. Well, we get out onto the galaxy, these particular gravitational waves would have an expected distortion of about 1 part in 10 to the 15. So if you go to a light year, which is the distance to the closest star, that's 10 to the 16 meters, over the distance between here and the closest star, or 1 light year, you're going to have a distortion of about 1 meter. And so that's the scale of what they're trying to measure here. And so over 10 light years, 10 to maybe 100 light years, you're going to see distortions in the shape of the galaxy or the plane of the galaxy.
Yeah. How do the pulsars reveal that?
Well, because as the shape of the galaxy is distorted, the timing of the pulsar getting from the pulsar to us is going to get shortened or lengthened. And by measuring that, you can't just measure, that pulsar, it gets longer or shorter, but by correlating that pulsar with that pulsar, you can now begin to get a measure of whether the shape or the space in the galaxy is being distorted.
Do the authors actually tell you the minimum number of pulsar measurements they need to detect this?
I haven't looked into the details. I was just kind of looking at, because there's, like I said, 4 different collaborations, and they've been doing this for, like I said, upwards of 20 years. It's clearly more than tens and probably less than 1,000, but I don't know the exact number. I'd have to go look into the details.
Just my gut feel is I would guess you would need to do these measurements on at least 1,000 pulsars to get a decent detection.
That would be my guess. I don't know what that number is. That would be an interesting number to go look at. And I know the more precisely we can measure the arrival rate, which better telescopes, newer telescopes are going to be able to do this. So anytime you do something over 20 years worth of data, you're dealing with changes in data quality just as our technology increases.
Well, what's interesting to me is we now have radio telescopes that are actually able to survey simultaneously literally hundreds of pulsars. Mm-hmm. So I think this is what's enabling this kind of analysis to be done.
Yeah, because if you had to just look at a single pulsar, you wouldn't be able to get these measurements. You got to be able to monitor lots. I don't know the details to know how wide a field, how many they're monitoring, but you're correct. There's got to be some minimum number to do that.
Right.
But what they're able to measure is, it seems like there's this evidence or a growing significance that should cross a threshold in the near future here, where we're seeing evidence of these gravitational waves that have wavelengths on the order of a few light years, which is pretty fascinating.
It is fascinating. Do the researchers actually speculate, what kind of events would generate wavelengths this long?
Their most likely scenario, again, there's multiple ways this could be, but one of the most interesting and most likely scenarios is that you've got massive black holes, supermassive black holes in galaxies. So the scenario is you've got a galaxy colliding with another galaxy. Each of those galaxies has a supermassive black hole. As they merge, the black holes will eventually merge.
Right.
And as they do, which is kind of an interesting physics problem that this arises, because when you do those studies, going back to your discussion about gravitational kicks, as these two black holes, massive black holes, are moving closer to one another, very often they would just kind of go right around each other, some sort of hyperbolic trajectory, or maybe they get bound and they're in some very wide orbit. But as stars come by, they get kicked out. Well, they're getting kicked out by taking energy from the supermassive black hole, which decreases the orbital distance of the black holes. The problem is that mechanism will work down to about a parsec. So you get down to about 3 or 4 light years, and there's no longer any stuff in there to cause those kicks. And so to get them to go closer than that is really hard. But if you do, eventually, as they start getting closer than a parsec, they start emitting more pronounced gravitational waves.
Right.
And so if there's a way to overcome this final parsec problem, getting down into that, eventually the gravitational waves start radiating away enough energy, and that will cause the massive black holes to get closer and closer until they eventually merge. So what the most likely explanation, although again there are other explanations out there, is that we're seeing the background of a whole bunch of these supermassive black hole binaries that are emitting gravitational waves, and they're distorting in a stochastic fashion the background of our galaxy, which is a cool discovery if that's what it turns out to be.
Okay, I got a question.
Yeah.
Did the researchers actually determine how many of these binary black holes must exist and how far away they must be to explain what we're seeing going on in our galaxy?
No, they haven't done that yet. One, because we don't know that we're detecting things yet. So this is really more saying, hey, it looks like we're getting close to being able to make this measurement. But it is thousands, if not more. And the fascinating part about gravitational waves is that they propagate in a measurable way over longer distances. So electromagnetic waves decreases 1 over r squared. Gravitational waves, for complicated reasons, only decreases 1 over r. And so the fascinating and exciting part about this is that by measuring three things I find fascinating. One, we're measuring gravitational waves again, which is cool because they were predicted for a long time and it took a long time to find them. Two, we're measuring them in a different spectrum or a different part of this wavelength spectrum than LIGO and the ground-based observatories are doing. So it gives us another handle on what's going on. But three, there is a problem using electromagnetic radiation to observe the universe, in that you get back to 400,000 years and there's this dense plasma that prevents any sort of electromagnetic radiation from penetrating beyond that. So using electromagnetic radiation, we have a boundary that we can't see earlier than 400,000 years. Gravitational waves don't have that boundary.
Right.
And so if there's stuff going on in that era, for example, like inflation or other interesting events, those gravitational waves would give us a way, if we can measure them reliably, to peer back further than our electromagnetic radiation would allow us. So that's still years down the road to do that. We're not like LIGO and the other ground-based instruments where we can say, oh, here's a gravitational event. This is this sort of merger event. Again, we're seeing a background, which is a conglomeration of a whole bunch of events. Like you said, thousands, if not millions of events. But we seem like we're getting close to we're kind of on the threshold of being able to say, yes, we can measure these gravitational waves. And then as we can measure them better and better with more and more precision, we can start to answer the kinds of questions you're asking.
Well, I see the potential of combining things like the LIGO measurements with what these people are doing to actually determine what is the density of binary supermassive black holes. What is the average density for the universe? Are we in a part of the universe where we're a little bit departing from that average density? These would be fascinating questions to investigate.
They are. The downside is I think it may be decades before we're able to answer those questions.
It might be a decade or two. On the other hand, the technology is already in hand to do that kind of exploration.
So yes and no, in that I don't know that the supermassive binary mergers would register in LIGO-type detectors because the wavelengths are just different and how it plays out. And again, I will emphasize where LIGO is finding, or again, the ground-based, I guess they're all ground-based, but the interferometry detectors like LIGO is, they're measuring individual events, whereas these pulsar timing arrays at this point are just measuring a stochastic background.
Correct.
So we know there's gravitational waves, can't locate the sources or strengths or anything like that.
But even if you're measuring the individual events, that's going to give you some idea of what's happening at a stochastical level.
Yes, I agree, but the types of events you're measuring are not the same types of
They're not the
events. With
same, right.
LIGO, they're solar mass type objects, whereas we're talking galaxy mass type objects with the background. But I mean, your point is well taken. That we're on the threshold of having this new kind of detection methods that will open up avenues that we couldn't even begin to explore before, just simply because now we can detect the gravitational waves, which we couldn't before.
But I'm going to have to wait till I'm in my 90s before I can write something about this as a fine-tuning argument.
It's possible. or one of the things that I find interesting about this is that this is a long-standing prediction of general relativity that there are these gravitational waves. I think they were probably recognized probably close to 100 years ago, and it's just been within the last 10 years that we've been able to detect them, the waves themselves. We've had indications from pulsars that they're radiating gravitational waves away.
Right.
So yeah, it may take a while, but also once we know what to look for and how to build it, it's finding stuff is harder than building the next instrument to detect it very often. And so now we know what we're looking for and what we're seeing. We can design specific instruments because we're looking in a known place as opposed to still trying to explore what's there. So it may go faster, but these are pretty large experiments. And I think something other than pulsar timing arrays is what we're going to need to get more details. But this tells us, again, assuming this does rise to the level of detections by all the instruments, or at least some fraction of them, it tells us that they're out there. And now let's go out and figure out, are they really supermassive binaries that are merging, or are they remnants from some cosmic event or cosmic stuff going on in the early parts, or are they something else? Are they cosmic strings? There's all sorts of cool ideas that we can now begin to explore. And I think it's just going to be fascinating over the next few years.
Whatever it is, it's going to be really interesting, and I think it's going to be a significant advance in basically revealing more fine-tuning. So
that's been the history as we open up new stuff. So
a lot to look forward to.
Well, very good. Well, I want to thank you for joining us today on Stars, Cells, and God, and I want to encourage you to get involved in the comments below and join our discussion. Remember to like this video, to subscribe for more content. New episodes of Stars, Cells, and God release each Wednesday and are available here on YouTube and on your favorite podcast app. Be sure to share this video with a friend, and remember, the more we know about science, the more reasons we have to believe.